continuing along with quantum mechanics stuff. And I've been doing, and I have a bunch of playlists on this so you can go look. Particle in a box, particle in a 2D box, and now we're going to do particle on a ring. Why are we doing particle on a ring? Because it brings in a lot of the important mathematical calculations that we need to do the hydrogen atom, which can get quite tough. So let's just do this problem. So here is our time-independent Schrodinger equation for in 2 or 3 dimensions. So we have our kinetic energy term, and that's the Laplacian del squared psi plus some potential. And this works only if the potential does not depend on time, and that's going to be equal to the energy multiplied by that wave function psi. The Laplacian in Cartesian coordinates looks like this. It's pretty simple. It's the second partial respect to x plus the second partial, it's an operator, plus the second partial respect to y plus the second partial respect to z. Now, here, this, if I do this for my x and y axis, I'm really kind of having some bad life choices there, right? Because how am I going to describe the motion here in the xy system how I'm confine it to this? It's possible to do it, but I'm going to have to do a 2-dimensional problem, and I'm going to have these constraints, and it's something I just don't want to do. I could instead use polar coordinates or spherical coordinates. Why would you use spherical coordinates? Because that's what we're going to do later. So in spherical coordinates, remember that we have 3 coordinates, r, phi, and theta. And so r is the distance from the origin to the point. Theta is the projection, the angle from the projection into the xy plane. And theta is the angle from the z-axis. Now, if this is in the xy plane, then I know that theta is equal to pi over 2. And if I'm confined to the ring, I know r is capital R, which is the distance from there. So I can kind of smash it down some, so that's kind of nice. But I do need the Laplacian in spherical coordinates. This is not an easy thing, but I'm going to write it down. So let's write down the Laplacian in spherical coordinates. My camera is really not behaving, and I'm not sure why. Okay, well, I hope you can see that. So in spherical coordinates, the Laplacian operator looks like this. 1 over r squared, the partial with respect to r, of r squared, the partial with respect to r. Right? That seems kind of weird, but it says that I take this and operate it on my function and multiply by r squared and then take the derivative again. Okay. Plus 1 over r squared sine theta, partial with respect to theta, sine of theta, partial with respect to theta. Again, let me just remind you that in a lot of math, you got to be careful about theta and phi, right? And or call it phi. You call it whatever you want. Just do it with confidence. In physics, we often have theta as the angle from the z-axis, and in math, they also often put the theta measured from the xy plane. So just make sure which one you're using. They're both fine. They're both acceptable. Neither of them are wrong. They're just different. Okay. And then I have my last term plus 1 over r squared sine squared theta, second partial with respect to phi. And that's my Laplacian in spherical coordinates. Okay, so again, we don't quite have a spherical problem. We have these constraints. So that's going to make it a little bit easier, right? If I have those constraints and I have r is constant and theta is constant, well, when I take the partial with respect to r of whatever function I have, it's going to go away. There is no change in r. When I take the partial with respect to theta, there is no change in theta. So I'm only left with this term right here. So I can replace this Laplacian in this case with this term. So I get negative h bar squared over 2m. And also I can put in r squared as r, and I can put in pi over 2 for theta, and the sine of pi over 2 is 1. So I get I know we're down here. I get negative h bar squared over 2m, 1 over r squared, and this just becomes the second partial with respect to phi, times the wave function phi, plus v equals e psi. So this is the equation that I want to solve, and that is indeed doable. So let's do it. Now, on our ring, we have no potential. So V is equal to 0. That means I can take this equation and write it as the following. The second partial of phi with respect to psi with respect to phi, and I'm going to multiply everything on the other side, is going to be negative 2m e r squared. I multiplied both sides by that. Divide by the h bar squared, and then I have that term psi. Is that right? Yeah. Okay. So I'm going to take the second partial of the derivative of this function and set it equal to this thing, which is the same function with that constant in front. So let's call this constant omega squared. So omega squared is going to be equal to, that's an omega, all of that stuff, the square root of 2m e r squared over h bar squared. Or I could pull the h bar out, that's fine. Okay. So now it's pretty easy, right? What function do I take the derivative of twice and get the same thing back with the negative sign? We've done that a bunch of times. We did that same thing for the particle in a box, right? The one-dimensional box. And we know we could use sines and cosines. I'm going to use exponentials. So you could say, let me write down my equation again right here. Partial squared of psi with respect to phi equals negative omega squared. No. Negative omega. No, that's right. No. Yeah, omega squared. Wait. No, that's omega. Omega is equal to that whole thing, not omega squared. So that's negative omega squared psi. So I could say, that's a pretty easy differential equation. So I could say that psi equals, let's put it like this. Psi as a function of phi is a e to the I omega phi plus b e to the minus I omega phi. It's a linear, it could be a linear combination of those two solutions, right? Because if I take the derivative of this twice, I'm going to get a negative, I can get I omega squared, which is negative omega squared, and there's going to be also negative omega squared, and then the a's cancel. But just to make things easier, let's just leave that term off, and we will be okay. Okay, so if I take the derivative of this once, I get a I omega phi. If I take it again, I do indeed get the correct solution. So that's my solution. Now, I do need to apply my boundary conditions. And this one's a little bit different. You may think, hey, it's just like a particle in a box, right? But it's not like a particle in a box. Number one, we have a slightly different function because we have that 1 over r squared. Two, our boundary conditions are a little bit different. So here's my ring, and here's my particle. And so it may have some wave function right there. It doesn't actually have a boundary. But if it goes all the way around and gets back to there, to the same spot, which is a angle of 2 pi, then the wave function has to be the same. Every time it gets back to here, the wave function has to be the same. So I can say psi of phi is equal to psi of phi plus 2 pi. That has to be true. That has to be true. So let's put that in. So here I have a e to the I omega phi equals a e to the I omega phi plus 2 pi. And the a's cancel. And I can write this as e to the I omega phi equals e to the I omega phi times e to the I omega 2 pi, right? Because I can write this as a sum of exponentials as a multiplication, like that. And again, those cancel. So I get this has to be equal to 1, like that. Now, if I want that to be equal to 1, what has to be true? Well, let's use the Euler equation and convert this back to trig functions. So if you remember, e to the I theta is going to be cosine theta plus I sine theta. That's true. That's the Euler expression. So this will be e to the I omega 2 pi will be cosine of omega 2 pi plus I sine omega 2 pi. And I want that to be equal to 1. Well, if I can solve this, if omega is 0, or plus or minus 1, or plus or minus 2, or plus or minus 3, okay, those are my solutions. Because if I put in omega equals 0, this is 1, so that's good, and that's 0. That's good. If I put in 2 pi, if omega is 1, I get 2 pi, so cosine of 2 pi is 1, sine of 2 pi is 0. If I put in 2, I get 4 pi, 1, 4 pi, 0. So you can see it works, and it works for the minus signs too. So that is my solutions. Now, that gives me conditions on the energy, okay? Because remember, this is how we get quantized energy. We don't get quantized energy from having energy, but instead from the boundary conditions. Okay, and in fact, a lot of times we call this ML, the quantum number ML, the magnetic quantum number. So if you see that, that's what that is. I called it omega before, but now I do need to find A, so I do need to normalize this. Let's normalize this, and then we'll find the energy. And then I'm going to plot it, because I like to do everything for you. Okay, so normalize. I know that the integral from negative infinity to infinity of psi star psi, and this would actually be, I guess, d phi, because I'm only in the phi space, has to be equal to 1. That's the probability density. Okay, the probability integrating over the probability density over all space has to be equal to 1. Well, I mean, my function only exists from 0 to 2 pi. And my time part, we've done this before, my time part's going to drop out. So I can just write this as a space part. So I can write this as the integral from phi equals 0 to 2 pi. And I don't know why my camera is cutting out. But I'm going to proceed. I'm going to power through psi star psi d phi. And now if I write, come on, man, stop this. Why is it so slow? Okay, well, I'm not going to do the Python stuff, that's for sure. So if I write this as psi star psi is going to be e to the I omega phi times e to the minus I, well, that'd be minus, plus omega phi d phi, right? And this is 1, because those cancel. So I get a pretty easy integral. Well, I have an a squared in their term, too. So I get a squared times 0 to 2 pi d phi is equal to 1. And that integral is pretty easy to do. It's just going to be 2 pi. That's a squared. So a squared equals 1 over 2 pi, or a is 1 over the square root of 2 pi. So now I have psi of phi is 1 over the square root of 2 pi, e to the I, I'll call it ml phi, where ml is 0 plus or minus 1 plus or minus, this camera's bothering me, 2, and so forth. Now what about the energies? So if we go back up here, this energy, we said was equal to omega. So I can square both sides and get an expression for, which I call ml. So I have, I guess I'll get a new piece of paper. So ml squared is going to be equal to, this thing. So ml squared is 2m e r squared over h bar squared. Now I can just solve that for E. So E equals ml squared, h bar squared, over 2m r squared. Now, and this is sub ml. This is important because I have degeneracy here, right? If I put in m equals -1 and m equals +1, I get the same value, right? Because I'm squaring it. So I have degeneracy here, and that is an important concept that we're going to look at later. The camera seems to be behaving, so I'm just going to go ahead and make a plot of the wave function in the ring just because it's fun in WebVPython. So let's switch over to WebVPython and make a plot, and that way I don't have to make a separate video. Okay, so I just want to plot this thing in WebVPython, and I will give you the code. So let's just start off with the graph. I'm going to copy this part. I've already done this part because there is one, and I'll show you what it is. There is one important point here that I do need to do. So I want to graph. I want to make a circle. And then I want to plot the wave function as deviations from that circle. Some people plot this in 3D with the wave function in the vertical, but I'm just going to do it this way. And to do that, I need to put a square graph so I can make it look like a circle. And if I need to put the maximum dimensions there so that it doesn't scale incorrectly and so it looks better. Now we do need some values, so let's go ahead and plot some values. R equals 1, phi equals 0, and my d phi, let's say 0.001. It doesn't really matter how big that is. Let's just go ahead and plot the circle while phi is less than 2 pi. What I want to do is calculate my x value. X equals r times cosine of phi. My y value, because I'm plotting in Cartesian coordinates, right? That's a little bigger. Y equals r times sine of phi. And then I can plot that. So I called that f1. f1 dot plot xy. Now I need to increase my value of phi or run forever. Phi equals phi plus d phi, and let's run that. I've been using Jupyter Python lately, and I keep hitting Shift Enter to run. So there's my circle. Okay, that's my ring. Now I'm going to plot the wave function as deviations from that ring. So let's make a function. We don't have to do this, but let's make a function, and I'm going to plot the real component, the real part of the wave function. You could plot both, but let's just plot the real part. So I'm going to define this as psi real, and I'm going to give it a value of phi and a quantum number. So I'm going to call this phi temp and ml. And then I'm just going to return the value, the deviation from that. I do need to, well, that's fine. A is 1 over the square root of 2 times pi. We don't actually have to normalize this. We're going to change it anyway. And I'm just going to return A times cosine ml times phi temp. That's it. That's all it does, right? So it's not too hard. Now down here, I can calculate, I'm going to plot my psi x and p, x and y. So let's calculate that. xp is going to be equal to, what I'm going to do is take my value, I'm going to add on to the r value. So my r for that plotting point is going to be a little bit bigger or smaller depending on the value of my real function. So it's going to be r plus the function psi r of phi, and let's plot the first one. So I'm going to use ml equals 1. I'm just going to put up here mml equals 1. That way I can just change it once. mml. Okay, that's my r value. Now I'm going to multiply that by cosine phi. And then I'm going to do the same thing for y. I'm calling it yp for psi. R plus psi r phi mml times sine of phi. And then I'm going to plot that. f2 dot plot xp yp. Let's see if that actually works. Okay, so it did work. It's a little. I'm plotting. This is space. I'm plotting a wave function in space, so I can really scale it down. Let's scale it down just so it looks a little bit better. I'm going to multiply this by 0.5, so it's half as big, just because I don't need to make it that big. Okay, so there's my ml equals 1. And you'll notice here's my ring, and then here's my wave function. And it does, no matter when I add 2 pi, I get back to the same wave function, and that's what I want. Well, let's plot the next, and that's the real part. Let's plot the next wave function, the next energy. So ml equals 2. And there you go, right? So you can see it's kind of a wave on a ring, which is cool. Let's just skip up to 6. Why go 3 when we can do 6? 6. There you go. That's what you wanted, right? There's your thumbnail right there. Okay. All right. So that's the particle on the ring. Really, it's an introduction to using these spherical Laplacian, the Laplacian and spherical coordinates, and we're going to have to do that for other things too. So, okay, yes, we're going to do some more two-dimensional, three-dimensional quantum mechanics leading up to solutions to the hydrogen atom, which can be quite complicated. If you want this code, I'll put the code down below, and that's that. Talk to you later.